Now that we have explored lines and planes in space, we're going to start taking a look at surfaces in space. And we'll do that by first looking at something called cylinders and traces in 3D. In order to understand the structure of surfaces in three-dimensional space, we're going to look at them through slicing. In other words, we're going to cut them in ways that allow us to look at them in two-dimensional space. We'll look at something called a trace, which is going to reduce a 3D surface to a 2D graph. And we'll see that a cylinder is going to have a slightly different definition in 3D space. Cylinders are going to be extensions of curves that occur in the plane into space. In three-dimensional space, we're going to define cylinders as anything defined by an equation that is independent of one of the variables x, y, or z. When we do that, we're going to be able to extend two-dimensional curves parallel to one of the axes in three-dimensional space. For example, if we think about the equation x squared plus y squared equals 4, we know in two-dimensional space this defines a circle of radius 2 in the xy plane. Because our equation doesn't contain z, that means that z can take on any value. So in three-dimensional space, the equation x squared plus y squared equals 4 defines the surface that is composed of all of the circles of radius 2 centered around the z-axis. This makes the shape that we typically think of as a cylinder. If we take the equation z equals x squared minus 1, this is a parabola in the xz plane shifted down 1. However, we can expand this into three-dimensional space by letting y, the missing variable, take on any number. When we do that, we get a shape that looks something like the one below, and this also is called a cylinder in three-dimensional space. To identify a cylinder, you're looking for an equation that uses two of the three variables x, y, and z. To recognize a cylinder then, we're looking for an equation that is missing one of the variables. That missing variable indicates the axis along which our cylinder extends. The cross sections of our cylinder parallel to that axis are identical, and the shape does not change along that axis of extension. Traces are what help us identify the cross sections within a cylinder or other three-dimensional surface. A trace is going to be an intersection with a coordinate plane. In order to find them, we're going to set one variable equal to a constant. If we consider our earlier cylinder, z equals x squared minus 1, we can see that its traces are a series of parabolas. And if we were to connect those traces with parallel lines, each of those parallel lines would be parallel to the y-axis. While in a cylinder, the traces are always parallel to the axis that corresponds to the variable that is missing, there are other solids that are not cylinders that have traces that are parallel to each of the axes. For example, take a look at this solid here. This surface comes from the equation z equals x squared over 16 plus y squared over 16, which is not a cylinder because it contains all three of the variables x, y, and z. We can get three different kinds of traces in an equation like this. If we replace x with some number c, we'll get a series of parabolas that are each parallel to the x-axis. If instead we replace y with c, we still get parabolas, but this time those parabolas are parallel to the y-axis. Replacing z with c gives us a series of circles, each of which is parallel to the z-axis. Let's take a look at a few examples. Here we want to describe this surface given by the equation x squared plus y squared equals 9. We'll notice that x squared plus y squared equals 9 represents in two-dimensional space a circle with radius 3 centered at the origin. Since we're in three-dimensional space now, we know that this is going to be a cylinder, and it's going to be parallel to the z-axis because z is the variable that's missing. So each of our traces is going to be a circle with radius 3, and its center is going to be on the z-axis. In this example, we have a surface that is not a cylinder, and I know that because I've got x, y, and z all in this equation. We want to find and sketch the traces of this. So what we're going to do is imagine what would happen if we let z be some number, x be some number, and y be some number, and what would the shape look like in two-dimensional space. So we're going to start off with we'll do the xy trace first. The xy trace comes from letting z be some number c. So if z is equal to c, then we know that the trace is going to be a circle with radius square root of c, centered at x is 0, y is 0, and z is going to be c. Notice here that if we let c be 0, then we have the equation 0 equals x squared plus y squared, which means that our trace is just the point 0, 0, 0. Similarly, if we choose c to be a negative number, the trace no longer exists because we cannot have a circle with a negative radius. Similarly, I'll switch colors to make this more apparent. We're going to do now the xz trace. This is when we let y be c. So there we're going to get that z is equal to x squared plus c. This is a parabola. It's going to be a parabola in the xz plane. Lastly, we can look at the yz trace, which is where we let x equal c. When we do that, we get that z is equal to c plus y squared, and this is going to be a parabola in the yz plane. I'm going to do my best to sketch each of these. So in this one here, if we have x, y, and z, we've got a circle of radius c. So each trace is going to look something like that, where imagine, I can't draw it very well. Hold on, let me erase this guy. And now I don't know that I'm going to be able to do what I want to do. Draw it. Yes. Through there. Nope, that's not what I want. I want it to look like it's going through this. So it's going to do something like that. There we go. So that axis is through the center, and this here is our value of c. So that's one trace. I apologize for my very, very lousy drawing skills. X, y, and z here. So this time our parabola is in the xz plane. So it's going to look something like this. And then in our last example, we're running out of room here. Now we're in the YZ plane, so our trace is going to look something like, it's very hard to differentiate between these last two because I'm terrible at drawing. But hopefully you get a sense of these. And you can also do this in applications like Desmos, where you just pick particular values for the variable who you're replacing for C, and you'll get to see what the traces look like that way. Let's go ahead and use Desmos to get a better idea of these. So here I pulled up in Desmos 3D my equation z equals x squared plus y squared. And to see the traces, what I'm going to do is in these brackets, I'm going to enter a value for z, a value for x, and a value for y, and we'll get to see what the traces look like. So if I just type in here, let's say z equals, I don't know, 3. Nope, that's too high. Let me do a different one. Let me do z equals 1. We can see that we get a trace there that's just a single circle with a z value of 1. We can swap that out now and let's look at, so that last one was the xy trace. Let's look at the xz trace. So this time we're going to let y be 1. And we see we get a parabola. If we change y equals 2, well, I think there it is. There's our trace. And we can keep doing that for different values of y equals 3. We'll get a slightly different trace. And then last, we can do the yz trace by letting x be some number. So we'll let x be 1, and we get that parabola. If we let x be 2, we get a slightly different parabola. If we let x be 3, we get a slightly different one. So you can see that by just changing the value of the of one of the variables, you can walk through the traces of this surface. Okay, one last example. Now we have the surface y equals x squared. We want to identify what that surface is in three-dimensional space and then what the traces look like. Well, this is a cylinder. Again, we're missing the letter Z, so we know it's a cylinder. This is what's going to be called a parabolic cylinder, and the reason why it's called that is because we only have traces parallel to the z-axis, and each of those is a parabola. So the traces are going to be parabolas. And because the original parabola has its vertex at the point 0, 0, the vertices of these parabolas are going to be at the points 0, 0, c, where c is any real number. So there's one parabola at any value of z equals c. So it will look, I don't know if I'm going to be any better at drawing this than I have the other ones. Let's do this. Let's do this is x, this is y. We'll make this c. So our parabolas are going to look like this, or our traces are going to look like this. All right, so the big ideas to walk away from this with are that cylinders are going to extend two-dimensional curves into three-dimensional spaces, that in the equation for a cylinder, the missing coordinate identifies your parallel axis. Traces slice the surfaces into familiar graphs. So when we look at a trace, what we're looking at is a two-dimensional slice of that three-dimensional surface. And last, in order to identify the traces, what we're going to do is substitute in x equals c, y equals c, and z equals c, and then identify the remaining curve that we get with those substitutions. Coming up next, we're going to expand our knowledge of surfaces in three-dimensional space from cylinders to include something called quadric surfaces.